Okay, so today we're going to continue with where we finished off at the last lecture. But I want to, before we start getting into the nitty-gritty, I want to make a few comments about where we're going with the course now. We've been looking so far in great detail at the way that molecules or atoms actually dynamically come together and how that coming together can be viewed on a potential energy surface. We can see how the energy changes during a reaction, and we can compute potential energy surfaces, or we can obtain experimental evidence as to why a potential energy surface might be the way it is. We did discuss, though, that although that's very nice and that's got an awful lot of very interesting chemical detail in it, most of the chemical information that we're really interested in, which is usually rate constants or perhaps equilibria or mechanistic details, doesn't rely on knowledge of the entire potential energy surface. And I gave you a few examples last time, where I emphasised to you that what we actually really need is the knowledge of the stationary points. We need to know about the reactants, the intermediates, the products, and the transition states. We don't necessarily need to know what's happening in between them. Now today, we're going to move on and see why that is the case. And we're going to, for the next few lectures, we're going towards understanding transition state theory. Now you may have come across transition state theory in first year kinetics in its fairly simple form. Transition state theory essentially complements the experimental observed Arrhenius equation. But the advantage of transition state theory is that it can be derived completely independently, and we can actually break apart the transition state theory itself in order to be able to compute rate constants just from knowledge about perhaps the reactant and the transition state. And the question is, what data do we need to know in order to be able to calculate a rate constant using transition state theory? And that's where I started us off at the end of the last lecture. And I drew up a potential energy curve. This could be for a diatomic molecule, this could be for a polyatomic system. And the key features of a potential energy surface around the stationary point. And the stationary point, remember, is all about around this minimum energy point here. So that value of R here is what I'm referring to as the stationary point. And what do we need to know along that line? Well, we need to know about the distribution of all of the energy levels. Last semester, Professor Whitehead taught you about statistical thermodynamics. And today, we're going to take what Professor Whitehead taught you, and we're going to take it one step further so that we can start to look at rate constants. So what do you need to know? Well, the first energy, after you've actually found your potential energy surface, the first energy level of any importance after that is a vibrational energy level. It's the energy level corresponding to V equals 0. It is the 0 point energy. And everything starts relative, in my course, relative to this 0 point energy. So the equations I'm going to show you, the statistical mechanical equations I'm going to show you, will start such that this bottom energy level starts at E0. That's my definition of E0 when I start showing you some of the equations. Now what else do we need to know? Well, you know that energy can be partitioned into translation, rotation and vibration. So the energy levels that are going to be possible all the way up to infinity are going to be either vibrational energy levels, rotational energy levels, or translational energy levels. So in order for us to understand the distribution of what molecules, how they will distribute themselves amongst these energy levels, amongst these energy states, we're going to have to invoke the Boltzmann condition. And at the end of the day, we're going to be looking for what is the sort of an average distribution. This is my value of U of T. At finite temperature, molecules will distribute them all the way up and down this ladder of energy states. We're looking for what's the average. What's the average energy? here. What is the overall energy of the system? And that is our definition of U of T. And that's what we started to do at the end of the last lecture. And the very first thing we noticed is that U at temperature 0 is very simply the potential energy that you would calculate the electronic energy of the system. This is where the electronic partition function would come in, is to define this value of E, plus the 0 point energy, then plus this correction. This correction here is the part we're going to now look at and think about. Overall, for those of you who've doing any, or have done or will do any electronic structure calculations, most computer programs will do this automatically for you. And what they will refer to is, they will refer obviously to the red potential energy. They will refer perhaps to this U0 as the adiabatic potential energy. And they will refer to this delta U of T, this temperature correction, they'll refer to that as a thermodynamic correction. So if you go through the computer output or on your screen, it will tell you about a thermodynamic correction. So let's go to the next slide. Now the next slide that I did right at the end was I looked at what is this thermodynamic correction. What does it consist of? Well, what we're interested in is the energy at a particular temperature is going to consist of a certain number of particles in the lowest energy level, plus a certain number of particles in the next highest level, plus a certain number of particles in the next highest level, etc., all the way to infinity. And I can write that as a summation sign with a subscript I, telling us that it's going to be this product of the number of molecules in state I times the energy of state I, or energy level I. Right, so where do we take it from there? Well, on page 36 and 37 of your notes, you'll find a very, very brief summary of what you learnt with Professor Whitehead. And what you learnt with Professor Whitehead was really that we can write, you learnt about the Boltzmann condition, and you wrote, if you follow the instructions on that page, you will be able to rewrite this equation as equal to n, which is the total number of particles, times the sum of EI, GI, e to the minus beta EI, all over the sum of GI, e to minus beta EI. So this summation always goes from 0 to infinity in all my cases. Now, I hope what you'll see now is I've left a gap there. I haven't proved that. I've said go and look at the particular pages in the notes if you're unsure and you can't find it in your original notes. Most of what I'm going to talk about today, and I'm going to write up a lot of equations today, I am not necessarily examining you on a proof. I have no particular wish to examine you on the proof of this equation. As far as I'm concerned, it's in your notes, yes, because that's important. You know that it is a simple step, it's a simple mathematical step. What I'm interested in this course is trying to extract from these equations some understanding so that you know where they've come from. I'm much more interested in you understanding and knowing the proof, for example, of transition state theory. But I'm not that interested in you knowing the proof of the statistical mechanical equations. I will point out to you that later on in today's lecture, which of the statistical mechanical equations you have to know. Okay, for the exam, I just want you to know a few equations. I don't need you to prove them, but I do like you to be able to know where they came from, because that'll help you to understand transition state theory and that it isn't all magic. It's not all just magic, it's very logical. So, there is a step which takes us from this very simple summation to this more difficult looking summation. What have we done? Well, the sort of thing that we've done obviously here, G is a degeneracy. We've allowed for the fact that it's much easier to write these equations if we, for example, take the rotational energy levels, and instead of counting them all individually, we group them together in degenerate levels. What else have we done? Well, we've now introduced, I hope what you can see here, this bottom denominator. This bottom denominator is, of course, something that you spent an awful lot of time worrying about last year. And that denominator, can anybody recognise it? Does anybody recognise that formula on the denominator? The sum of the exponential of all of the energies.
Arrhenius equation?
Not quite. It's very related, actually, but it's not quite.
Partition function.
Partition function, thank you. You had 8 lectures to grasp the idea that this is the magic number. This is the magic number that describes the entire molecular energy. It describes everything about the distribution of energies in a molecule. It's the magic number. As I always tell my tutees, it's a bit like that holy grail of number 42 in Hitchhiker's Guide to the Galaxy. That number G, here, G, but it's not G, is it? It's a Q. Okay? That letter Q is a magic number describing the molecular system you have. Well, that's very nice. What else do we need to know? Well, I can add in here, if anybody here is really on the ball, they might recognise what this top part here is. And that top part, well, obviously I've got an N here. N is the same. I'm not going to lose the N. But anybody who's really on the ball might recognise that this term, written green, turns out to be dq by d beta. It's the derivative of q with respect to beta. And that really simplifies it. Actually, it's the minus, because I need to add a minus sign there, because we have a negative exponential. So that horrible looking equation, so you go from here to something that is truly looking monstrous, back to something that is very, very manageable. It's a derivative of q with respect to d beta, the number of particles total, number of molecules, divided by this magic partition function. And that really is the key. Remember what we've actually calculated here, delta U of T. Delta U of T. This is our thermodynamic correction. It turns out to be dependent upon the partition function. So that bottom equation is obviously a very nice thing. If you're ever asked to describe all this stuff, maybe not in my exam question, but if you are, that's a very nice equation to hold on to. Now, I can actually go a little bit further with that. I can actually take it one step further. Get my piece of paper. I can just take it one step further, and a little bit of jiggery-pokery, and you can write that down as equal to, so delta U of T, a little bit of manipulation, and you'll be able to see that that is actually minus n d log Q by d beta. Now remember, beta equals 1 over kT. Now this is another thing in my course. I am rather loose with some of my nomenclature, in the sense that when I'm talking about molar quantities, I really ought to use R, the gas constant, instead of Kb. If I'm talking about molecules, then I'm going to stick with Boltzmann's constant. So at this stage, I'm just talking about molecules, so I'm going to rewrite all these equations in terms of Kb. But when you come to exam questions, and there's a very nice little piece in the frequently asked questions explaining this to you, when you have to put numbers in these equations, undoubtedly they're going to involve molar quantities. And the simple thing you all have to do is to replace the beta, this Kb, by an R, just like you did last year if you were on the ball. So this is a very nice equation. Now delta U is now the derivative of the log of Q. That's actually just a bit of manipulation and understanding here. And I have to say I've got an at constant volume, I have an extra bit of equation which I'm not going to go into and tidy that up. Right, so we've got a very nice equation now we can work with. Where should we go from there? Well, I want to introduce you, just to remind you, and let's go for the translational energy. This one is particularly important in the Eyring equation, in the transition state theory. This is a really important term. That should be an E, by the way. My fat pen is not making it easy. Okay. So what do we have with the translational energy? Well, E translational is equal to E translational in the x direction plus E translational in the y direction energy plus E translational in the z direction. Because motion is in each of the three directions is independent. I'll zoom in a bit. Zoom in a fraction. So how are we going to write that form? Well, let's write down what the partition function should be. E translation. So let's just work in one dimension. Let's just work along the x direction, just for the moment. So let's just work in the x direction, and let's write down what is the partition function. And the partition function is a sum over all states, that infinity sign. All states are I, and we're going to have E. I'm not going to worry about, there is no degeneracy here, so we won't worry about it. Okay. And I'm going to have, that's just my simple partition function formula, E to the minus beta times the energy of each translational energy level, I. Very nasty looking equation. The question is, how do I solve that sum? How do I actually do that? Well, what I would like you to understand is the way that we can do that is we can recognise that this formula, EX here, could be written as a particle. You could treat translation as a particle in a box. So our particle is moving up and down in the dimension, or one dimension of a box. It's obviously going to be fixed by some walls at either end of the box, but that particle moves up and down inside the box. And if it does that, because it's in a box, it has a whole series of discrete quantum energy levels. So this actually, the use of the particle in a box is actually very, very useful. So, sorry, I've got E of I, so I squared, H squared, you don't need to worry too much about, over 8 times the mass of the particle times Li, the length of the box, in the x direction squared. So we have a formula because we can treat this as our molecule being in this box with walls, moving up and down, and because it's trapped, we get a series of energy levels, and those energy levels go to infinity. We have a formula. How do we actually then solve this and get a very, very simple formula for it? Well, like I always try and think, the best way to solve a summation formula is obviously, when you're summing, if you can make your energy levels very, very close, or the things you want to sum very, very close, then you can always replace the summation sign by an integration sign. So let's replace the summation sign with an integration sign, because, and we can do that because the energy levels are very, very close together. You can see why I'm just writing it all out. It's really not 8mLx squared. And then we'll have dni. There we go. So we can replace it by an integral. It's the same formula. All I've done is I've replaced my summation sign by an integral sign. So I've actually got now, I'm assuming quite correctly that the difference between these energy levels, these energies, is very, very small. And that's a good approximation for translational energy levels. Anybody like to do that integral for me? Right, well, let's just skip it and let's give you the answer. again, I'm not particularly interested in that. I can put it in a textbook. That will actually turn out to be 2 pi, the mass of the molecule, all over beta times h squared, or to the power of a half, times the dimension of the box. All right. So some mathematicians done that for us, and it just shows what we've managed to do is we've managed to reduce something that's very, very difficult to sum into something that you can sum analytically with a nice formula, and it results in a formula that we can all quite happily work with. Beta, pi, beta, Planck's constant, the mass of the molecule in the box, and the size of the box. Excellent. What about in 3 dimensions? We can actually do the same thing, and you'll find that in 3 dimensions, Q trans will equal 2 pi m all over beta h squared, and this time in 3 dimensions it will be 3 over 2, and it will be Lx times Ly times Lz. Would anybody like to tell me what the length of a box times the height of a box times the depth of a box is? The volume of the box. Fantastic. So this turns out to be a volume. And this is where we have a problem now when we come to look at rates. Rates of reaction and anything else associated with thermodynamics. I think you're all aware, when you think about thermodynamic quantities, you often invoke concentrations. It's all to do with the concentration of products over concentration of reactants. Well, what are the units of concentration? Moles per dm cubed. There's an inherent introduction of some volume into the whole process. And this is the origin in the statistical mechanical world of the introduction of the volume part of our chemical world. So translation and the translational energy levels and what translation a molecule can do depends upon what space it has to move around in. And that's very important. So Q translation here is very, very important here. Q trans equals something times V. So usually the units of a partition function are unitless, but this partition function will have the units of volume. So because that has Q trans has the units of volume, what we really often want to do in statistical mechanics is to get rid of that volume, and we can write, and this is the final part, what we're going to often do is we're going to write this as Q trans over V, and that will equal 2 pi m, the mass of the molecule, h squared, beta, so that's 1 over kT, to the power of 3 over 2. And this is called the translational partition function, per unit volume. So, this is going to be very, very important, because when we come to look at rate constants, quite a lot of, if you have, for example, a rate constant, you're going to have, does the first order rate constant have units involving volume? Does anybody think ahead of that one? It doesn't. So somewhere on our journey now into rate constant land, we're going to have to get rid of that volume, because obviously that's going to have to go somewhere, and it's usually a sticking point for most students, is where does this volume go? Where does it come from, and where does it go to? Well, it comes, as I've shown you, as part of Q trans, but we're going to try and work with this very simple formula and try and get rid of it later on. So that's the translational energy. Oh, I should just point out, if you want delta U of t, what do you have to do with that? You need d log q by d beta. So if you can take the derivative of that, you will end up, for translational, q translational will lead to a value of half RT per dimension. That's another thing. When I the final equation that you use to correct and to actually use delta U of t, how do you correct your energies? You'll suddenly find that I am just saying, oh look, if you have half a value of RT per x, if you have x, y, and z, it's half RT is the energy, thermal energy in the x direction, half RT thermal energy in the y direction, half RT thermal direction in the other direction. This doesn't just magically come from anywhere, it comes from what we've already just talked about today. We've learned what the Q trans is, you take the derivative of the log with respect to beta, and it gives you this really, really simple formula. So, in fact, you will actually, when it comes to adding thermodynamic corrections, you don't need to worry about 2 pi m h squared over beta. You only have to worry about a very, very, very trivial formula. And it's going to turn out that in exactly the same way, rotations have exactly the same result. Delta U of t, a rotational contribution, will also turn out to be half RT per rotational degree of freedom. These are very, very simple formulae to learn. Is everybody okay so far? Our journey. Right. So, at the end of all of that, where do you get? Right. This is where these formulae are presented in your notes. These are the ones you're going to use when we talk about rate constants. These, I'm afraid, are the ones you will have to memorise. This page should have a big box around it saying, must learn again. So what have we got? Well, the first thing we're going to remind ourselves is that the total partition function for a molecular system is the product multiplied translation by rotation by vibration by electronic partition functions. Very important that this is going to be the hub of our description, because we're going to describe the energy of a particular of the reactants, and we can do that individually by looking at translation, rotation, vibration, electronic parts, and simply multiplying them all together. And I have summarised for you the 4 equations you need. Now, the first one, the electronic partition function, you can practically forget. That one is not going to be particularly useful in this course, because all the problems you're going to be given are going to be such that the ground state of your molecular system is very dominant, and the excited state is a long way away and isn't going to interfere with our problem. So put a little cross by it, because it's going to pop out in the way we do it. It'll just pop out, but don't really worry about the detail of it. Vibrational partition function looks horrendous here. So what does the pi sign mean? Somebody remind me, what does the pi, big capital pi sign? Big capital pi, what does it mean? Or what did a big capital sigma mean in the formula? Sum. Good. Big capital sigma down here, anywhere else up here, meant a sum. Big capital pi means the product. So instead of adding together each term in a summation, we multiply them all together. So let's have a look at what we're multiplying together. It looks horrendous, but let's have a little look down there. It's probably not so obvious. It's minus hc nu bar I. So nu bar I is one of the vibrational frequency wave numbers of your system. It's the ith vibrational wave number. It is, after all, a vibrational partition function. So this is the ith vibrational wave number. So we can plug that into this formula. We can plug in the first, calculate that term, and we do that, and then we multiply that term by plugging the second one in. So this whole formula will equal, so if I can just, it'll be 1 over 1 minus e to the minus, I'm just going to very abbreviate it here. I'm going to put nu bar 1, and then it's going to be multiplied by 1 over 1 minus e to the minus nu bar 2, dot, dot, dot. So you're going to work out that term for each vibrational, for all vibrational modes. This is going to be very interesting because you know that for a molecular system there are 3n-6 vibrational modes. That means there must be 3n-6 terms in that equation. But what about a transition state? Are there 3n-6 modes in a transition state? What does it all mean? That's what we're going to be talking about in the next lecture. So this is fine for the reactants. We're going to have to do a little bit of work to understand that for a transition state. Rotational partition function. Pretty easy, really. Q rot is 4/8 pi squared. The moment of inertia is I. Boltzmann constant Kb. Temperature all over Planck's constant squared. So all you need to know there is that I is the moment of inertia. You only need to know formula for a diatomic. And we'll talk about that later in the workshop. The formula for for a diatomic molecule is something you've learnt last year, but I'm not going to present it here and clutter up our screen. It's there in the problem. If it's more than a diatomic molecule, you don't have to worry about it. And we've just done the translational partition function, and m is, of course, the mass of the molecule. So they're actually they look horrendous at first, but actually when you look at them, they are very, very similar, and they actually, the vibrational partition function require the vibrational frequencies. The rotational partition function requires a moment of inertia, which requires to know the geometry of the molecule. And the translational partition function just depends upon the mass of the molecule. Key feature is they are all temperature dependent, obviously, and they're all very, very computable if you have those three key bits of data. So there we are. There's a summary of how we do it. This is how we calculate the internal energy of a molecule within the Born-Oppenheimer approximation. I summarised this at the beginning of the lecture. I told you the first thing we have to do is add on the 0-point energy. Let me just do that again. Got a nice clean one here. So, what do we have? Remember what we said before? We have E of R, our potential energy. Then we have U of 0, where we add on our 0-point energy. Here, that's our 0-point energy. So we've done that, that's our 0-point energy. And then we have this extra, we have the full U of T, which is going to be the sum of all of these energies, each the translation, rotation, vibration, electronic. And here are some very key formulae that you would need to do the problem. So, as I mentioned, I showed you the origin of these. You need to know that the translational energy at finite temperature, you would add on 3/2 RT, half an RT in each dimension. For rotation, it's slightly different because we have a non-linear case or a linear case. Really, it's a half RT in any dimension, but a linear molecule only has two rotational axes. So that's easy. You've only got two lots of half RT. Translation, hopefully you're translating in the X, Y, and Z, so you have 3/2 RT. And a non-linear molecule, 3/2 RT. So we can add on all of these components in these formulae. The only complicated one is that bottom one, the vibrational one. It's the one that was in the last year's exam question wrongly. So don't expect me to give you it ever again, because it was a right pain. It's my fault. I gave that formula wrong in the exam, because I was trying to help you all. So I'm sorry, it'll never happen again, because trying to help you turned out to be a nightmare. So you have to remember it this time, if you ever need it. What are the key features of this, find the equation for the vibrational energy? Remember that this bit here is the 0 point energy, and this bit is the rest. That's the rest. So that energy just reminds you, oops, sorry, I've zoomed in and then I do that, don't I? Okay. Right. So, when we're calculating the energy due to vibration in the molecule, we are, remember, starting from the electronic energy, so that's the 0 point energy part, and then we have the rest going from U of 0 up to U of T, and that's the rest part here. And notice that that these formulae are all written in slightly different ways to get the units right. So Na there is the Avogadro constant, so that we can get everything in per mole. So I've tried to keep all of these formulas. I'm using R instead of Kb, and I'm adding this Avogadro constant Na to make sure everything is in per mole. Because after all, we're only really interested in energies in per mole. Now in your notes, there is a numerical example of how to do this. If I have time at some point as we go through the course, I will go through part of that example. So that example should be on about page, let's find it in your notes. There we go, page 53, example 1. Page 53, example number 1. And I talk about the chemical reaction of H2 dissociation, H2 going to H plus H. And all of these formulae are used and expanded to calculate these energies. So there's an example there, a very simple example on how to use the formulae. And hopefully we'll go through that at a later time. But I want to concentrate a little bit more now on the theory, on why we're doing things. Are we okay so far-ish? Use the word ish because I'm sure everybody is a little bit or wondering what on earth I'm going to ask them. Okay. What's the next step? The next step is really moving us towards transition state theory. This is why I wanted to just start here. So we now know about how to calculate the energy where we start. And we now know how to calculate the energy of the transition state, again, correcting for finite temperature. So I've given you formulae which can calculate the value of those brown dots, the energy of the reactants and the energy of the transition state at finite temperature. And these formulae require you to know the partition functions. Excellent. Now, what does transition state theory state? Well, transition state has a number of very, very simple assumptions, and I guess the first assumption that we've now can tick off is this first one, is that the distribution of molecules amongst the energy states will be according to the Maxwell-Boltzmann distribution. So we've got translational energy there, Maxwell is in there, and that's all that's saying is that we're going to be able to use partition functions. Partition functions tell us about the distribution of molecules amongst their energy states. So transition state theory assumes that that will be the case for our reactants and for our transition state. So good, we've already done that one. We didn't even know we were doing it. What's the next most important aspect of transition state theory? Well, transition state theory says that in order to calculate the rate constant for this chemical reaction, A plus B, going through a transition state AB dagger, there is going to be an equilibrium between the reactant and the transition state. It says nothing about the products whatsoever. We say nothing about the products. It is an equilibrium between the reactants and the transition state. In other words, so many reactant molecules will go towards the transition state and then we'll maintain that equilibrium. It's a bit like the steady state approximation, but the rate of this reaction is going to assume that these two states here are states, are thermodynamic states. And thermodynamic states, we can say, they are in equilibrium. It's an equilibrium theory. You can prove transition state theory without assuming this equilibrium. So it's not a particular restriction, but it really makes life very, very easy for us to understand if we start out by assuming that there is this equilibrium. Because now what we can do is we can start to say, well, if I've got a distribution of states known here and a distribution of states known here, does statistical mechanics allow us to say anything about equilibrium constants? Did you do equilibrium constants with Professor Whitehead? No? I don't think you didn't do it in the past. So our next step is going to be have to take our distribution of states here and our distribution of states here and use those two distributions of states to get an equilibrium constant. Because if we've got an equilibrium constant, we can then proceed with transition state theory. There are other assumptions for transition state theory which will become very important next time. This particular one is that as soon as you get to the transition state, the rate of crossing the transition state, as soon as you get to the transition state, there's no going back. It's a one-way process. Basic transition state theory says once you get to the top of the mountain, you're going over, and that's it. No turning back. Every reaction goes on to products. It's a very, very fundamental part. Now, there are extensions to transition state theory, we'll see, which can relax that somewhat and allow you to recross, to go back and backwards and forwards. And particularly, the rate at which you reach the products is therefore proportional to the rate at which you cross this transition state barrier. So when it comes to a rate constant, the key feature will be that once you get to the rate to transition state, the rate at which you cross it is the rate of the reaction. So there are two aspects to the problem. One is getting to the transition state, and we're going to assume an equilibrium. And the second thing is once we've reached the transition state, how fast do you cross it? How fast do you go over it? Because that's proportional to our rate constant. Right, so the very first part, the rate constant, the equilibrium constant. How do we write an equilibrium constant in statistical mechanics? Well, let's have a quick look at that. A, equilibrium, and B, yes. The first thing I need to assume here in my picture I'm going to have two states. I'm going to have a state A, and I'm going to have a state B. And I'm going to assume, today, I'm going to assume that delta H, so this is potential energy, so I am going to assume that delta H equals 0. So I'm going to assume that those two states have the same potential energy. And then we're going to say, well, let's give the left-hand side some energy levels. And let's give the right-hand side energy levels, but we're going to have the energy levels, we're going to have them twice as closely spaced. Okay? So on the left-hand side I've got 3 energy levels. On the right-hand side, in the same energy space, I'm going to have 6 energy levels. And I'm going to ask you, what would the equilibrium constant K be for that picture? What do we need to know? Well, the first thing, let's think about delta G. Delta G is minus RT log of K. K is the equilibrium constant. So the log of K is equal to minus delta G over RT. Good. And the log of K is going to equal minus delta H over RT plus delta S over R. So that's our first starting point, just to help us through. So if delta H is 0 here, then the first part of the term is going to disappear, and log K is going to equal delta S over R for this example. So that gives it a relationship. Log K is delta S over R. So now what we need to do is to delve into statistical mechanics and find out what does statistical mechanics say about entropy. Well, in this case, there's a very, very simple formula. And this is why this subject is not hard. It's very hard to derive it, but it's very beautiful to see the result of it. And it says that the change in entropy of this system is the ratio of the two partition functions, QB over QA. So we can immediately write down that K is equal to QB over QA. The equilibrium constant is always simply the ratio of the partition functions. A very, very simple, elegant proof, just to get you to something that actually is incredibly simple and useful. Equilibria are directly proportional to partition functions. So let's have a quick look in our example and see if that works. Does that work for us? Well, QA and QB. Well, can we write down what QB is here? Equals how many QA? Well, let's just remind you what Q is. Partition function. It's the number of thermally accessible states. Okay, isn't it? It's the accessibility of those states. Number of thermally accessible states. And here, at a particular temperature, let's say that's our temperature there. Within that amount of thermal energy, that amount of energy, how many states can I reach on the right-hand side? I can reach 6 states. On the left-hand side, I can only reach 3 states. So the number of states I can reach in B is equal to twice the number of states that I can reach in A. For the same amount of temperature, for the same amount of thermal energy. Substitute that down here, 2QA over QA equals 2. So the equilibrium constant here has a value of 2. The right-hand picture, the right-hand molecule B, because it has this greater number of states available, the equilibrium is very, very firmly to the right-hand side by a value of 2. It feels logical. I hope it feels logical. I hope you see that I'm not just plucking. I could have plugged this formula out. In fact, on the next slide, on the first slide you'll receive next time, I could have just plucked this out of thin air. But I think it's quite nice to think about that it's not daft. It actually, equilibria, all thermodynamic properties do have these very simple connections to accessibility of states. I think that's an absolutely perfect place to start.